Hello and welcome to 50 conceptual questions answer video series. Already we have discussed four questions, and here is the fifth questions. And these questions are basically related to the Fraunhofer diffraction pattern. So let's see what we have to solve in this problem. Here it is written, a light passes through a narrow slits and give the Fraunhofer diffraction pattern shown in the adjacent figure. Which of the following could be the shape of the slit? So what is written here? We have a diffraction pattern of some unknown shape of slits. So looking at this diffraction pattern, we have to guess which of this following option or which of the following shape could be the shape of slit which will give this diffraction pattern. So to solve this problem, we have to understand few things. First thing, what is diffraction? What is diffraction? What is diffraction? So to understand that, let's assume we have a narrow slits of slits width B, and we have a screen which is placed just behind the slits. And then if we illuminate these slits with a plane wave, then what we'll observe? So according to geometrical optics, one can say that the region A to B, this region will be fully uniformly illuminated, and apart from this, all the other parts of the screen should be absolutely dark. But if we take a carefully look on this experimental setup, when the wavelength of the incident wave is almost nearly equals to the width of the slits, then we'll see the intensity distribution on the screen. Not only light will confined within this region AB, but it will also goes beyond of this region. That means light will spread in the geometrical shadow region, and also the intensity distributions in this region A to B will not be uniform. And it has been observed that the intensity distributions will look like this. At some point intensity will be maximum, at some point intensity will be minimum, and this. And it's also observed that more you make narrow the slits, the more amount of energy will spread the geometrical shadow region. So this phenomena is called diffraction. So then what is diffraction? So the spreading of light when it passes through a narrow slits is called diffraction, and the pattern that create on the screen, that pattern is called diffraction pattern. So in this case, this is called diffraction pattern. Diffraction pattern. Okay. So this phenomena is called diffraction, and this intensity distributions on the screen is called diffraction pattern. Then usually we divide this diffraction pattern into two categories. Diffraction pattern into two categories. One is called Fresnel diffraction and another called Fraunhofer diffraction. Fresnel diffraction and Fraunhofer diffraction. Fraunhofer diffraction. So what is the difference between these two diffraction patterns? So in Fresnel diffraction, usually we place the screen and the source of light at finite distance from the slits. So in Fresnel diffraction, source of light and screen are placed at a finite distance from the slits. So how this schematical figure will look like? So will look like this. Let's say this is our slits, and then we'll put light source at a finite distance from the slits, and we'll also put the screen at a finite distance from the slits, and light will get spread like this. So this phenomena here also light spreading out through this narrow opening region. So this phenomena is also called diffraction, but this diffraction phenomena is known as Fresnel diffraction. This is also known as near field diffraction. And we have another type of diffraction which is called Fraunhofer diffraction. In Fraunhofer diffraction, both the source and screen both are placed at infinite distance from the slits. But usually we do this experiment in our lab. So how it is possible that we can place this source and screen at infinite distance? So for that we do something to optical engineering. So what we how we'll make this experimental setup? Let's say we have a slits width. This is the slits, and then we have a point source here, and if we place this point source at the back focal plane of a convex lens, what it will create when this light that will be generated from this point source, and this light when it passes through the convex lens, it will create a plane wavefront like this. And the observer, who is, let's say, standing on the slits, you will see a plane wavefront, and she can imagine that that source is actually placed at infinite, and that's why the wavefront that is coming from the source is plane wavefront. Okay, so in this way we can place this source at infinite distance, but this is not exactly infinite distance, but placing this lens, we are assuming that this source is placed at infinite distance. And on the other hand, just after getting diffraction the light from the slits, we put another lens here. So again, this parallel rays will get converged at the focal plane, and at this focal plane, if we place a screen, so again a parallel ray can converge at infinite distance, but in this case, by placing this lens, we are actually converging this light at the back focal plane. So again, we can say this screen is placed at infinite distance. Okay, so this is the case of Fraunhofer diffraction. So usually we just place this second lens just behind the slits. So this distance between slits and screen is written as F. F is the focal length of this lens. Okay, so these are two types of diffraction pattern. One is Fresnel diffraction, another is Fraunhofer diffraction. Fresnel diffraction is also called near field diffraction, and Fraunhofer diffraction, which is also called a far field diffraction. Okay, now this Fraunhofer diffraction pattern can be generated for a single slit as well as multiple slits. But for this study, only for today's problem, we will consider only single slit diffraction. single slit Fraunhofer diffraction. Fraunhofer diffraction. Again, the shape of the slits could be different, like it could be rectangular, it can be also circular shape. So in this case, first case, we are assuming that the shape is rectangular shape. Rectangular shape. Okay. So let's draw a schematical diagram. Let's say this is the slit plane. And we have placed a slit here. Let's sit here. Whose width is B. So this is the slit plane and this one is slit. And then if we illuminate these slits with a plane wavefront, and on the other side of the slits at a distance f from the slits, we'll get a diffraction pattern. So let's say this is our screen. So on the screen, we'll get a diffraction pattern. So when a rectangular slit is illuminated with a plane wavefront, usually we get a diffraction pattern which will look like this. It will be look like this. So I'm not going to derive this mathematical expression what will be the intensity of the diffraction pattern. That I will do in next video series, where I will upload a complete lecture series of electromagnetic theory. There I will derive this mathematical expression of diffraction diffraction pattern. But for today's problem, we just assuming that we know this how to write this mathematical expression. Let's say this is the incident of intensity of the incident wave, and let's say slit width is B. Slit width is B, and this angle let's say theta. So this is called diffraction angle. Then at this point on the screen, what will be the intensity? That is the diffraction intensity of the diffracted light, and the diffracted intensity can be written as I is equals to I naught sine beta divided by beta whole square. Divided by whole square, where beta is equals to pi divided by lambda into b sine theta. What is lambda? Lambda is the wavelength of the incident wave. So this is the intensity distribution when the rectangular shape slits is illuminated by a plane wave, and if the slits width of the slits is b, then at a position theta on the screen, we'll get an intensity, and that intensity can be written as I naught is equals to sine beta divided by beta sine whole square, where beta is equals to 2 pi by lambda into sine b sine theta. Okay, and if you draw this intensity distribution, you'll get like this pattern. Okay, and also for if we want to draw a diffraction pattern for a circular shape slit. So diffraction pattern. Diffraction of circular slits. So I can assume that this is our slits plane. This is the slit plane. And now we have a slit of circular shape. I have a slit of circular shape. So only this portion is opening and all other portion are actually closed. Okay. And in this case, let's say assume the radius of this circular aperture is A. The radius of this circular slit is A. And then again, if we illuminate these slits by a plane wave, then we'll get a diffraction pattern of these slits on the screen. Let's say this is our screen plane. This is our screen plane. So in this case, intensity pattern will be look like concentric circle, dark and white circle like this. Dark and white like this. And again we can derive the intensity distribution on the screen plane. But for this problem, I am just directly writing this mathematical expression of the intensity of the diffraction pattern. For that, let's say assume intensity of the incident wave is E0 and the radius of the circular slit is A. Then at any point on the screen, we consider a point P, and if this point makes an angle theta with this vertical line, then this angle is called diffraction angle. So at this point, intensity can be written as I is equals to I naught first order Bessel function and then beta divided by beta whole square. In this case, what is beta? Beta is 2 pi by lambda into A sine theta into A sine theta. And what is lambda? Lambda is the wavelength of incident wave. Okay. So this derivation we'll discuss later. So apart from this derivation, what we can say here, if we have a rectangular shape slits and then if we illuminate, so we'll get an intensity pattern like this. And if we have a circular shape and if we illuminate this circular shape with a wavelength, whose wavelength is of the order of radius of the circular aperture, and in this case we'll see the diffraction pattern look like this, and in this case intensity distribution can be represented by this mathematical expression. Now what I will request to do all of you, we'll do a simple few mathematics, step of mathematics. We know the definitions of Fourier transform. So if we have a rect function, how we define rect function? Rect x, y, a. What does mean? That's mean this function, value of this function will be 1 for x less than a by 2 and greater than minus a by 2, and for other value of x it will be 0. So this is called rect function. So if this is x-axis, this is y-axis, then if we draw this rect function, it will look like this: minus a by 2 to plus a by 2, this will be 1, and other part it will be 0. Okay. And then if we take a Fourier transform of this rect function, we'll get another function in Fourier domain, and frequency domain. So what will be that function? So for that, what we have to take the Fourier transform of this function. So let's take the Fourier transform of this function. And if this Fourier transform of this function is, let's say, f, capital F, and it's function of Fourier frequency, spatial frequency fx, and that can be written as minus infinity to plus infinity, and then this rect function into e to the power minus iota 2 pi x into f of x into dx. Okay, and then if we put this rect function here, so when x will goes minus infinity to plus infinity, but this limit of x is minus infinity to plus infinity, but this function will be 1 only for minus a by 2 to plus a by 2. For other part it will be 0, so we can write here, okay, minus a by 2 to plus a by 2, and then 1, this rect function will be 1, so simply 1 into iota 2 pi x f of x. And then if you integrate this, what you will get? You'll get a sine function divided by this term, because we have to integrate with respect to x, so we have to divide 2 pi f of x. So what we'll get here? We'll get here sine pi a 2 will cancel out, so a f of x divided by pi f of x, pi f of x. And then if we multiply a denominator and numerator, so what we'll get? A sine pi a f of x divided by pi f of x. So if we write this pi f of x some another variable, let's say beta, then what we'll get? We'll get this Fourier transform of the rectangular function FFT of rect x divided by a is equals to some constant a and then sine beta divided by beta. So now if I take the square of this Fourier transform, what we'll get? If we write square of this Fourier transform, we'll get a f of x. We are taking square of this Fourier transform, and this will give you a square into sine square beta divided by beta square. So now take a look on this mathematical expression of this Fourier transform of this rectangular function, square of this Fourier transform of this rectangular function, and the intensity distribution, the mathematical expression of the intensity distribution when it is diffracted by a rectangular slit is almost same. But this I naught, if I equal to I naught with this s square, then remaining function, here it is sines in diffraction pattern, you can say sine square beta divided sine beta divided by beta whole square. Here is also you are getting a sine square beta divided by beta. So from this simple mathematics, what we can say that the intensity distribution intensity distribution of a single slit Fraunhofer diffraction is equals to square of function of the slits. Function associated, oh, not function, Fourier transform square of the Fourier transform FFT. FFT means Fourier transform, first Fourier transform of safe associated Fourier transform of the function associated with the shape of the slits. Okay, so this is the main idea you need to know to solve this type of problem. This is the main idea that you should know to solve this type of problem when examiner asks you what will be the diffraction pattern associated with this slit shape. Okay, so what is the main concept? The main concept is the intensity distribution of a single slit Fraunhofer diffraction will be square of the Fourier transform of the function associated with the shape of the slit. That we have also noticed here. We have a rectangular function, and then when you take the Fourier transform and when you take the square of this Fourier transform, exactly get the same expression as we'll get this expression for a diffraction pattern for rectangular slits. Okay, so using this concept we can solve this problem. So whatever shape will give you, whatever the shape of the slit that will give you, and if the examiner asks you what will be the diffraction pattern of this slit, what you have to do, you have to write the mathematical expression associated with the shape of the slits, and then you have to take the Fourier transform, and after taking the Fourier transform you have to take square. If you take square, and then this function will give you the diffraction pattern. So using this idea and using some, because I am at home, so using I have a laptop, so I have access of laptop, and using MATLAB code, I have already produced some diffraction pattern associated with different shape of the slits. So here, if we have a rectangular slits, then we'll get a diffraction pattern like this. This is nothing but just what I have done. I have created a rectangular slit, and then I have taken the Fourier transform of the slits, and I have drawn here the square of that Fourier transform. So what you have to observe here, that when you have a rectangular function, rectangular slits, you will get a diffraction pattern like this, and in this case light will spread always perpendicular to the direction of slits, length of the slits. So this is the length, this is the length of the slits, so you have to draw a perpendicular line to the length of the slits, and then in the diffraction pattern light will spread in this direction. Okay, and similarly if we have a circular slits, and again I have using MATLAB I have created this pattern also. So I have created a circular slits, and then I have taken the Fourier transform of this, and then I have taken the square of this Fourier transform, and I get this shape. So again, this is the diffraction pattern as I have seen here also in this circular aperture I have already shown here. So if we have a circular aperture, we have a diffraction pattern like this. So exactly same figure we also get here using this software. So the main idea is whatever the shape of the slit, if examiner asks you what will be the diffraction pattern, what you have to do, you have to write a mathematical expression associated with the shape of the slits. Then you have to take first Fourier transform FFT, and then you have to take square of this Fourier transform, and that will give you the diffraction pattern associated with this slit. So using this idea, we can solve this problem, and I have already drawn this different diffraction pattern associated with different shape that is given in the questions. So in the option we have L shape, Z shape, plus shape, and S shape. So if we take if we want to draw the diffraction pattern associated with L, so again what you have to do, you have to produce a L-shaped slit, and then using MATLAB you can produce that, and then you have to take the Fourier transform this, and then if you take the square, you'll get a diffraction pattern like this. So this is the diffraction pattern associated with L-shaped slits. And then I have also generated this diffraction pattern associated with plus shape, and then also associated with Z shape, and then also I have generated this diffraction pattern associated with S-shape slits. So looking at this fourth figure and looking at the diffraction pattern that is given in the question, so from there we can say that this L shape will give this diffraction pattern. So our correct answer will be L. But wait 1 minute. So I am at home, I have an access of computer. So I have generated this shape and I have generated this diffraction pattern using laptop, using some software. If these questions asked in the exam, where you may not be get the access of computer, then how we will draw the diffraction pattern associated with this shape. So for that, the main idea you have to remember that if we have a rectangular shape, then the diffraction pattern will be sinc function, and that pattern, to draw this pattern, what you have to do first, let's say you have L shape slits. So what you have to do, you can consider that this L shape is generated, it's produced superposition of two slits. One is this portion, and another is this portion. So for this portion, what you can do draw a perpendicular line to the length of this slits, and then light will spread in this direction. So you'll get diffraction pattern like this. And then for this slits, again, this is also a rectangular function. So this will also give you a diffraction pattern in this way. So this will produce this. But here you can see when you compare this L and plus shape, this plus shape is also superposition of two rectangular shape, but both the rectangular slits are symmetric here. Because of that, you can see the diffraction pattern is also symmetric in X and Y direction. But here, this L, this portion is not symmetric, and because of that, this layer is also not, this layer and this sinc function is not symmetric. And then if you take a look for Z slit also you can assume that it's a superposition of three rectangular slits. One is this portion, another is this portion, and is this portion. So for this portion, here to here, this portion, if you want to draw a diffraction pattern, how you can draw? Again, you have to draw a perpendicular line to this length, and then you can see, you can draw like this. This will be the intensity distribution along this line. And then for these two lines, they are parallel. So this will give you a diffraction pattern in this way. So exactly same here, you can see that diffraction pattern is generated here. So using this idea, you can write what will be the diffraction pattern associated with Z shape, and also for S shape. For S shape, again you can see that this portion is almost a rectangular function. So for that, if you draw a perpendicular line this in this direction, so intensity will be distributed this direction. Here you can see this is the perpendicular line, and this direction have sinc function, one sinc function. And there will also be some circular part, because this portion and this portion, they are circular shape. So in middle you can see there are some circular shape also. So using this idea, you can find out the diffraction pattern for simple slits, simple shape slits, like as I have shown here, L shape, Z shape, S shape, or also you can find out diffraction pattern for T shape or I shape. But if examiner give you a complicated shape, then definitely they will give you some access of computer where you have to do the same thing. First you have to write the mathematical expression associated with the shape of the slits, and then you have to take the Fourier transform, and then you have to square this, and that will give you a final result. So I hope you understand how this diffraction pattern and the shape, intensity distribution of the diffraction pattern and the shape of the slit are related with each other, and from there how to draw this diffraction pattern. So enjoy it. We'll see you in the next video. Till then, bye bye.